Not to be one who rests on his laurels, Einstein kept working on physics. His laurels were impressive enough by 1905, but in 1907 he starts to think about, well, he was probably thinking about it beforehand. You know how that Einstein brain was. They've got it preserved. Creepy. Okay, so what I'm saying is, in 1907, he started wondering about this equation, F is ma, Newton's number 2, and the force of gravity, which was m times baby g. And he thought it was interesting that this mass right here, that upper mass, this is what I would call inertial mass. And this mass right here is what I would call gravitational mass. And these two masses happen to be exactly the same thing. These equations are different, and there's no reason they should both be m, but I could call this m sub I, and this is m sub g. They don't actually do that, but because there's no point, because they are exactly the same. So this tests an aspect of the equivalence principle, and that aspect is, well, if these two are the same, then we can get this really cool conclusion that says if something's in free fall, you know, if something is in free fall, the only force acting on it is gravity, then we can say that net force is the force of gravity. And since inertial mass is equal to gravitational mass, then we get that the acceleration of something that's in free fall is baby g, which is the strength of the gravitational field, but it also has units of acceleration, and it is in fact the acceleration of something in free fall. So a lot of people call this the acceleration of gravity, or the acceleration of free fall, or free fall acceleration. You know how people are. They like to call it all kinds of things. But he eventually wrote some crazy stuff. Like, this is a great foundation, but now I want to point out that if you're in an elevator, let's get an orange elevator. Yeah, it's got like shag rug walls. If you're in an elevator and you suddenly, the cable breaks, you've got two things to do. You need to, number one, get your life in order. Because that cable just broke, and you are accelerating with baby G down. You are accelerating. So, number two, you might wonder about the amazing physics that you're experiencing, because it's kind of like you're not feeling gravity. Here's my point. If you're in free fall, and you're in an elevator, you can't tell the difference between that and you being in an elevator in outer space. And if you're okay with this, things are gonna get really crazy really soon. But if you're not okay, ask me a little question right here, because I need you to believe that if the elevator cable breaks and there's no friction on the sides or anything and you're accelerating at baby G, you frankly can't tell that there's gravity at all. So sensing gravity is kind of like having something act against gravity. The reason that you, sitting there at your computer, think there's gravity is because your chair is pushing up on your bum. Are you standing up? Oh, that's kind of cool. You got one of those walk-in desks. Are you on a treadmill? Cool. But something is pushing up on you, presumably. Wow, you should watch this video in free fall. That would be very interesting. But if something's pushing up on you, then you know there's gravity. If nothing at all is pushing up on you, then you don't know there's gravity at all. In fact, especially if your surroundings are also accelerating with you. If everything's going down at baby G, then you can't tell what's going on. A lot of people call this 0G, and the point is, you can't tell that there's any gravity. That's why they call it 0G. You are weightless. Wait a second, are you weightless? Of course you're not weightless, but wait, you also don't feel your weight because you don't feel gravity. Is that making any sense? I don't know, I'll say wait again. Wait, no, let's stop waiting, let's go on. What's even more shocking is this. Here's what's shocking. Einstein says, and this is what we're going to call the equivalence principle. There are lots of cool names like the Galilean equivalence principle, the weak equivalence principle, the strong equivalence principle. And we're going to call the equivalence principle this. An accelerated reference frame. Oh, do you remember special relativity? Special relativity was considering only those special circumstances in which we were in inertial reference frames. So we're leaving that little box right there, and we're moving over to accelerated reference frames. An accelerated reference frame can be made that mimics, and when I say mimic, I mean completely mimics. I want to mimic gravity. Or let me be a little bit more firm about this. I'm going to say that can mimic the presence of a gravitational field. Of a gravitational field. You can create a virtual gravitational field by accelerating something. And by extension, of course, a gravitational field exists when you accelerate something. So this is kind of flipping the previous discussion on its head. And I want to point it out to you like this. Let's have an elevator. And there's a guy in the elevator. And the elevator is not accelerating. All right, this guy right here is in the elevator, and the elevator is not accelerating, but the elevator is in space. Elevator in space. Okay, and also, well, that's kind of like being in a gravitational field, but also accelerating down. So you've got gravitational field, which is kind of like an acceleration up, and an acceleration down, which kind of cancels it out. So that's kind of, I don't really like that one. I want to think about this. If you're in an elevator in space, and instead somebody is making you accelerate up at baby G, what if you accelerate up at baby G? And I don't mean you go up. I need to really think about what acceleration means here. This means every second you're going up by 9.81 meters per second squared more. I mean 9.81 meters per second. You're going 9.81 meters per second upward every second faster. Faster and faster upward. That's the accelerating elevator in space. The cool thing about this is this elevator in space that's accelerating upward at baby G is exactly indistinguishable from this elevator that's on the ground. If it's sitting here on Earth and you are inside of this elevator, you frankly cannot tell whether you're in a closed box on Earth or you're in an elevator in space. Remember we said in the bathroom of a jet, you can't tell that you're on a jet and not in the ground. So this is kind of related to that, except I'm stepping it up. And I'm not saying just special relativity with velocities. I'm saying accelerated situations. Accelerating upward is the same thing as being in an elevator in a gravitational field. So that's very, very interesting. I'm going to give these guys flashlights, okay? I'm going to give a guy a flashlight. Do you believe this? These are the same? Every physical experiment cannot tell these two apart. And if you want, we can go into more detail about that, but I'm gonna assume that you guys are beginning to believe me, that these are exactly equivalent. You will have the floor pushing up on you with force that's equal to your weight in this situation, and the same thing would happen over here. Same. I give this guy a flashlight, and no, let's give him an electric torch. And it's pointing that direction, and the light comes out, and I'm gonna assume now that this acceleration is really, really much bigger because I need something interesting to happen. If he's accelerating upward, then the light won't follow a straight path because the light that left a long time ago is gonna be hitting the wall a little bit lower than the light that is leaving right now. The light that's leaving right now is coming out of the flashlight right there. And it's going horizontally, but remember the elevator is accelerating up, so more and more and more it's going up. So it is if the beam bends like this. It makes a parabola. Exactly as it would if you were like shooting a water hose or something horizontally. But this, I mean, this is a little bit crazy. You're not gonna actually get that kind of bending of a beam of light. You will get bending of a beam of light, but you won't be able to notice it in baby G. But what if we were accelerating way faster or something? You could imagine that there is, strictly speaking, no longer a straight path for this light. The light is going out straight, but the fact the elevator accelerating up more and more and more leaves the time for this, as it's traveling to the wall, to actually be left behind by the elevator, which is going faster and faster this direction. This is not true for a fast-moving upward elevator. It's only true for a fast accelerating upward elevator. Don't confuse velocity and acceleration right now when I really need you. Careful now. Here's the problem. If you give this same guy on Earth an electric torch and you say, hey, shine that at the wall, we argue by exactly the same thing, these are the same situation, that the light will also bend in a parabola, unnoticeable for normal course of human events because we don't have very big accelerations. But guess what? A very big acceleration is equivalent to a very big gravitational field. What? Are you telling me? Are you telling me that light feels gravity? That gravity affects light? Yeah, I am. Doc Schuster, I don't like that because I thought that light didn't have any mass, and you're right. Light has no mass. No problem. So if you don't like the fact that light has no mass, and therefore the force of gravity on light is m times the acceleration of gravity, and therefore it's 0, that's fine too. But there is a bending of light in a gravitational field, and you could just say that, well, gravitational fields curve space-time. That's fine. How about that? Gravitational fields curve space and time. Does that make you happier? Sorry you asked, right? That's what Einstein ultimately concludes. And you're going to have to deal with this. The presence of mass, which creates gravitational fields. Well, mass bends space and time itself, which causes light, therefore, to bend, because this light is just following a straight path. In fact, space itself curves downward because of the presence of Earth below this guy. And this is following a curved path because it's an accelerated reference frame, but you can't tell which one you're in. So we're left with the equivalence principle that this accelerated reference frame is exactly identical to this gravitational field right here. In fact, well, this was really, really frustrating to the scientific community. They were like, what? And so people got really interested. They were like, maybe. And so they sent an expedition to Africa. And by 1919, check this out. In 1919, there was a known solar eclipse. So they went to Africa. Awesome. Hi, all viewers in Africa. They went to Africa and they discovered during the solar eclipse that if the sun was there, usually you can't look at the stars right behind the sun, but it was cool with the solar eclipse. You had darkness here in the sun, and maybe you had a little bit of corona or something that you could see. I don't know. That doesn't really matter. What I'm saying is that there were some stars over here that appeared to be near the sun, and I don't have any idea what they looked like. But the cool thing is, 6 months later, those same stars were still in the sky, of course, but the sun was on the other side of the Earth. I mean, the Earth was on the other side of the sun, right? So if we look at these stars, we wouldn't see the sun in the way. And the thing is, the position of these stars, let me see if I can kind of draw these, but not exactly. The position of these stars were different. Every position of the star was different because the presence of the sun had bent the light from the stars. I'm going to take a side view of this. This is us looking at the sun, and there's an eclipse, and we're looking at that pattern of stars. Imagine like this, though. Here's the sun, and here's us observing the universe on Earth. That's the big eye on Earth, and Earth is actually a lot smaller compared to the sun. But over here there were these stars, and the cool thing is the stars that we were seeing should have been behind the sun, and therefore light blocked by the sun. But light came out from these stars in every direction. Every one of these stars emits light in every direction, so some of that light went right into the sun. That's fine, and that's what would usually have met our eye in the case of like 6 months later. But I'm saying it went like this. Watch this. It went woo, because the light from the stars felt the gravitational field of the sun and bent as a result of that. Light feels gravity. Or if you don't like that, you're gonna have to accept that space and time itself are bent by the presence of this gravitational field right here. Wow, gravity bends space-time. So, that's cool, right? I like it. So a lot of people call this the acceleration of gravity, or the acceleration of free fall, or free fall acceleration. You know how people are. They like to call it all kinds of things. But he eventually wrote some crazy stuff. Like, this is a great foundation, but now I want to point out that if you're in an elevator, let's get an orange elevator. Yeah, it's got like shag rug walls. If you're in an elevator and you suddenly, not to be one who rests on his laurels, Einstein kept working on physics. His laurels were impressive enough by 1905, but in 1907 he starts to think about, well, he was probably thinking about it beforehand. You know how that Einstein brain was. They've got it preserved. Creepy. Okay, so what I'm saying is, in 1907, he started wondering about this equation, F is ma, Newton's number 2, and the force of gravity, which was m times baby g. And he thought it was interesting that this mass right here, that upper mass, this is what I would call inertial mass. And this mass right here is what I would call gravitational mass. And these two masses, you know, if something is in free fall, the only force acting on it is gravity, then we can say that net force is the force of gravity. And since inertial mass is equal to gravitational mass, then we get that the acceleration of something that's in free fall is baby g, which is the strength of the gravitational field, but it also has units of acceleration, and it is in fact the acceleration of something in free fall. This happen to be exactly the same thing. These equations are different, and there's no reason they should both be m, but I could call this m sub I, and this is m sub g. They don't actually do that, but because there's no point, because they are exactly the same. So this tests an aspect of the equivalence principle, and that aspect is, well, if these two are the same, then we can get this really cool conclusion that says if something's in free fall,